Hi. So we're gonna go more deeply into the idea of quantum computation and how to match this uh, s- practical scheme for quantum computation with the relevant mathematics. That's kind of the goal of this lecture and a couple of lectures that will follow. So when we talk about classical computation, we typically think of doing things like simple addition, two plus two equals four, or the same operation in the binary system will be 10 plus 10 equal to 100. Yeah, so something of this sort is what comes to our mind when we talk about the classical computation. But then the phrase quantum computation does not really bring anything to our minds because we have not really seen anything like this before. So first of all, let me set out to say that quantum computation is basically the same as a bunch of unitary operations on a state, on a n qubit state. Okay, so let's say we have these n qubit system, the physical qubits. Each qubit is represented by this little box, 1, 2, 3, 4, up to n. And then we already talked a lot about doing a unitary operation on a single qubit. Okay, so you can think of each qubit as some sort of a spin half or a two-level system. And the unitary operation on a single two-level system is represented by some matrix of this form with arbitrary real number alpha and arbitrary unit vector n. So any matrix, two by two matrix written in this form is a valid unitary operation acting on a qubit. So that was the lesson. However, we also learned that it's possible to perform a two qubit unitary. So, in principle, you can have a one qubit unitary operation, but you can also do a two qubit unitary operation or three qubit unitary operation, and so on. There's no limit on how many qubits you can act on simultaneously by appropriate unitary operation. However, in practice, of course, one qubit unitary is a lot easier to implement than a two qubit, which is a lot easier to implement than a three qubit unitary, and so on. Okay, so the goal is to do everything in terms of these most simple kinds of unitaries. And as I said before, if you only perform the one qubit unitary operations, you're never going to be able to entangle the different qubits. So already from that argument, it's clear that you need at least a certain amount of two qubit unitaries, and the hope is that you don't really have to go to the three qubit unitary operation to entangle the states in an interesting way. And I'm going to argue that, in fact, you don't need to use the three qubit unitary. In fact, everything can be done in terms of one and two qubit unitaries. Okay, so what I mean by that is that you can create any quantum state you want by employing a whole bunch of 1-qubit unitaries and a whole bunch of 2-qubit unitaries. Okay, but anyway, at the moment, these are just my words, and what I mean by these will become clear as time goes on. Okay, so typically, the quantum operation starts with the initial state, which is a product of zeros. Okay, so every qubit is set to be in the same state, which we'll, for convenience, just call the zero state. So everything is in a zero state. And the overall quantum state is a direct product of these 1-qubit states. And then you perform some unitary operation on this, which will generate a new different state. And on top of that, you perform the second stage of a unitary operation, which will give you yet another state, and so on. So by applying a whole bunch of these unitaries, the final state will be obtained. So let's say you apply p layers of the unitaries on the initial state. Then the whole situation will be described by a product of these unitary operators acting in succession on the initial state, which is a simple product state. All right. So what is the content of each of these unitary operations? Well, as I said, this each unitary operation consists of a whole bunch of 1-qubit operations and 2-qubit operations. And of course, it's a lot easier to talk about the 1-qubit operation, so that's what I'm going to do. So the 1-qubit operation breaks down in terms of these 4 elementary operations. The first one is the identity operation, which means that you do nothing to the existing qubit. But there has to be, of course, more interesting kinds of operations, such as this X operation. So this do nothing operation has the matrix representation, which is, of course, 2 by 2 unit matrix. And this flip operation has the matrix representation, which is the well-known Pauli X. Operator like this. And this is also known as the NOT operation, for an obvious reason that whatever the state is, the action of the operation is to reverse that state into the other one. Now, the other one, the other kind of 1-qubit operation is the Y operation. Okay, and in terms of a matrix, this is 1 and minus 1, which is minus I times sigma y. So there's this extra phase factor of minus y. But up to this phase factor, this is basically the Pauli matrix sigma y. And the third operation is the z, which has the matrix representation of sigma z Pauli matrix. Okay. So, of course, this sort of operation can exist classically, and so does the X operation. So both the I and X are well-known classical operations, but these two are not really classical operations at all, right? The reason is that the when this operation acts on the one state, it returns the zero. So on the face of it, it looks just like the ordinary not operation. And also, when you act on the zero, it returns 1. So that also looks like an ordinary not operation. But one must keep track of these thing here, minus thing here, which also means that not only do you flip the state from 0 to 1 and 1 to 0, but there's a sign change associated as well. Of course, this sort of sign does not have any meaning in classical systems. But in quantum systems, the sign of the wave function also matters. So that's why this operation is not the same as the not conventional not operation. And by the same token, this is not the same as the identity. Although on the face of it, it returns the 0 when it acts on the 0 state, returns the 1 when it acts on the 1 state. But the important thing is that when it returns 1, there is an overall phase factor of -1 involved as well. And that's what makes this a Z operation different from the identity operation. So again, this distinction arises because in quantum mechanical states, the sign of the wave function also matters. Okay. But it's also the case that the most general kind of unitary operation is expressed in this mathematical form. But I also proved to you some time ago that they can break down as this form. And using the notations I introduced just now, this part is just cosine alpha times the identity operation. And the other parts are nx, x operation, plus ny, y operation, plus nz, z operation. So what happens is that arbitrary one qubit operation is literally a linear combination of those four elementary operations I, x, y, and z. Okay. Okay. So and also we know that these three operations has a matrix representation which is equivalent to the three Pauli matrices. So the Pauli matrix has important role not only in the theory of spins, but also in the overall theory of quantum computation. So whenever a two-level system is under consideration, the most ideal framework, mathematical framework to talk about such a two-level system is the Pauli operator algebra. That's why these Pauli matrices keep popping up. All right. So as I said, every one qubit operation is a linear combination of these four, or maybe I should say these three, because this is really not an operation at all. This is just doing nothing. But nevertheless, people talk about these particular linear combination of these XYZ operations with a special name, Hadamard, or sometimes called Walsh-Hadamard operation. But let me just save some time and forget about this other person because most commonly this is known as the Hadamard operation, and it's called H, not to be confused with the H in the Hamiltonian. And its matrix representation is this. Okay, in other words, this is the linear combination of a x and the z operation. Okay, so when this Hadamard acts on the 0, it returns a linear combination of the 0 and 1, like this. And when it acts on 1, it returns the other linear combination of 0 and 1 with a relative minus sign here. Okay, so this is nothing special. This is just, this is what people would normally call the change of basis. Okay, and in fact, out of this general thing, you can choose alpha. You can choose alpha to be quarter of pi, and then let's see, and then n would be. Let's see, what's it gonna be? And then n would be. This is pi over 2, not quarter pi, but half pi. And then n would be square root, like that. In that case, this cosine alpha becomes 0, sine alpha becomes 1. And so that the unitary matrix becomes I, and square root over 2, sigma x plus sigma z. So up to this trivial phase factor of I, this is exactly the Hadamard unitary operator I talked about. Sorry, maybe I should say this is U of H, because this is really a unitary operation. Okay. So after all, this Hadamard operation is nothing but a special case of this general one qubit unitary. So then the question is, why do we have to make a big deal giving it a special name and all that? Well, the reason why it's rather special, H is special, may be seen from the following. So when you act with the Hadamard on a single qubit, of course you get this sum of the two states. But when you do the Hadamard on a 2-qubit product state like that, so that the first Hadamard acts on the first qubit and the second Hadamard acts on the second qubit, and schematically that means you hit this first qubit with some Hadamard operation. The second qubit also gets hit by the same Hadamard operation. And the end result is the rotated state product, rotate state product, which when you write it out will be the sum of the 0, 0 state and 0, 1 state, 1, 0 state, and 1, 1 state. Okay, but notice that this is the sum over all possible all state. This is sum over all the possible states of 2-qubit cluster. Now, it's now quite obvious what will happen if you do this for the 3-qubit cluster. 3 H's acting on the 3 zeros. Well, it's a little bit long to write down, but let me exercise some patience and try to write everything out. So this is a sum of the all possible 8 possible states: 0, 0, 0, 0, 0, 1, and 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. And obviously this trend is going to continue. And what will happen for the n qubit cluster acted on by the n Hadamard operation is sum over all the 2 to the n possible states of those bases. Okay, so now I have this single letter x to represent all possible 2 to the n possible basis states going from 0, 0, 0, 0 to 1, 1, 1, 1, all the way to the end. Okay, so this is a quick way of literally bringing out every single state in the Hilbert space. Bring out every state. And this is not a trivial statement because the number of states in this Hilbert space is exponentially large, 2 to the n. And by doing this Hadamard, you do not get to miss any of those because now every one of those states participate exactly once in this linear combination of the n-qubit Hilbert space. Now, but what does that help? Why does that help? What does it mean for quantum computation? In what ways does that help with the quantum computation? In principle, it could help with the quantum computation vastly. Because say you had a system like this, n qubits, and attached right next to another m qubit cluster, and then you get to do an Hadamard operation only on this subset of the qubits. The result would be and while keeping all of these states in the m qubit cluster to be in the 0 state. So the result of performing the Hadamard only on this subset of the qubit cluster is would be the following. So you have this usual combination of x Okay, so this is a simplified notation for the state of these m qubit cluster, where each qubit is in the 0 state. Okay, So this is symbolically written down by a single zero over here. And now let's assume there exists some sort of unitary operation. Let's say U exists, and what the U does is when it acts on this combined N cluster and the M cluster system, is to alter the state of the M cluster and throw it into a different state, which I represent as f of x. So in obvious implication is that this f of x is somehow the functional value of this function f when the input value happens to be one of these 2 to the n binary digits. Okay, so this operation is literally computing the functional value of f of x. And this is not a trivial thing when you have exponentially large number of possible inputs, exponentially large number of choices. Okay, so you bring out your fastest working computer or calculator, and then for x equal to, let's say 1000112 1110011, whatever f happens to be, let's say 3, maybe one single calculation is quite fast. But if you have to do this for an exponentially large number of x values, then the task will going to cost you an exponentially long time. Okay, which is often the reason why the classical computers will fail to perform certain calculations within a reasonable time frame, because it simply costs too much time, exponentially large time, to complete the calculation. However, if you generate such a state and then do this U operation on such a state, then the consequence of doing that is that, okay? So just as we were able to generate all possible choices of the variables, okay, there are exponentially large number of choices for the variable x, and we were able to generate them all because of the Hadamard operation. Now, because we were doing this unitary operation on top of such a state, now every possible functional value of fx is also generated. And what you had to do to generate all possible outcome of f of x is this single unitary operation. In other words, one unitary operation or calculation can find all of the functional values of a given function. So it's kind of like having an exponentially large number of computers that are running these calculations in parallel. So one computer computes the value of fx for one choice of x. The next computer computes this value for the next choice of x, and so on. To accomplish that in using the classical computer, you literally have to put together an exponentially large number of computers and give them different inputs. But once you have a quantum computer, then you just have to have one quantum computer to perform those exponentially large number of operations at once. Okay, and this is really the essence of why people are dying to make a quantum computer, because this sort of computational advantage is something that you can never ever hope to achieve with classical computer. It's not a matter of not being clever enough with the classical algorithm. It's it's just the inherent character of the classical computation that you're not going to be able to perform this many exponentially many operations at once. And but this is something that quantum computers are sort of naturally built to do.